because two particles, when they shoot out like this, right? So you can't measure distance between them. The distance changes as you go along them. You want to measure an angle between them, right? Well, you want to measure an angle between them. You measure it in phi, because that's invariant, and you can measure it in eta, because differences in eta are invariant. And so whenever we deal with angles, which we do a lot, we deal with phi and eta as our angles. Unfortunately, when we deal in the real world, then we have to work in theta, right? So in real life, we build at this angle, but the calculations we do all work at this angle. Okay, because of this, now, because of this fact about eta being the same, what happens is when particles come out, they are distributed evenly, not evenly in theta, which is non-lorentz invariant quantity, but evenly in eta. So when we build our detectors, we care about eta, not theta. Wow. So we care about pseudo-rapidity when we build our detectors. All right. Woo! So what does this all mean? Well, it means that when you build things, you care about eta. Now, how does eta work? If you don't want to feel like doing the math, here's how eta works. This is the z direction. Okay. Straight up perpendicular to the z-axis is eta equals 0. Okay? Eta equals 1, you can calculate it exactly where it is, but it's around here. And then what happens is here's eta equals 2, and then 3, and then they start to bunch up. And eta along z, eta exactly along the z-axis is equal to infinity, that's right. So here is eta equals infinity. Okay, so you can see that eta up here makes a big difference. When it gets down here, they kind of bunch up. Going this way, this is eta of -1, and so forth, going down the other way. All right, so eta equals 0 is like your sweet spot where the best events go. But in a sense, those are also the easiest ones. You want to get as much coverage of eta as you can. So when you subdivide your detector, when you split it up into pieces, you would split it up according to eta, right, to segments in eta. So that means that they will not be evenly sized segments. As you go forward, the segments will get smaller, and that's normal, that is sensible. It matches the behavior of the relativistic particles. So this is how you break things up. Okay, so we mentioned yesterday, I want to emphasize again, you have to break your detector into pieces, right? So let's say this is a side view. Here's the beam pipe, and here's your tracker, as seen from the side, right? And then around the tracker, you have a calorimeter. Okay? Now, for the standard design, a sampling calorimeter, what does it look like? What's it made of? Yeah, well, let's just focus on, say, the econ for a moment. What's the econ made of? Good, it's alternating layers of absorber and scintillator, right? So you'll see layers, it'll look like this going out, right? Layers alternating of scintillator and absorber, right? So like scintillating plastic, say, and iron or something like that, right? I forgot to mark it on the document, but you can't put iron inside a magnetic field. Right? Right. So watch out for those. You can, other metal, brass works okay, lead works fine, but iron is ferromagnetic. You cannot put it in a magnetic field. Bad things will happen. So if you're building, if you remember I said you had the option of putting the magnetic field on the outside, if you do that, you may, but no iron inside, right? That would be very bad. The other metals are all fine. It's really iron that's the problem.
Can you stick iron on the outside?
Iron outside of the magnet is no problem. Okay, so it's going to be layered like this from the side, okay? But then also, you can't just have one giant slab of scintillate, and then going out, typically you do it in discs. So you'll have things layered out like this. Okay? That's the most common way to build it, yes.
How would you do this for a spherical?
You'll have to decide.
Dagnabbit.
What?
Nothing.
He's complaining because he has a sphere design and he doesn't want to try to.
We have a sphere design too.
Yeah, I know. Yeah, I know.
All right. You could in principle build these as spheres as well as cylinders. I would say why not, right? But the segmentation is important. So you can't just have one giant slab of scintillator, like all the way across the detector. Why not? What would be the problem with that?
It needs to be.
Yeah, you get like all the particles going through it, right? So you get 50 particles hitting it, and all you get is their total energy. You have no idea which one's what. So in order to be able to figure out which energy goes with which particle, what do you have to do with the colorimeter? You have to segment it, right? You have to break it into pieces so that when a particle hits, it hits just this part, right? And then you know the energy goes with just that particle. You still, of course, could have more than one particle hit one spot, but it's a lot better. And of course, then, if you have a lot of particles going on, then what do you want in your colorimeter? How do you want to segment your colorimeter? More like finely is the word, right? You want to split it up into smaller pieces. The smaller the segmentation of colorimeter, then the higher resolution you have, the more able you are to distinguish between different particles. But what is that going to do for your cost? Why will it make your cost increase? It's the same amount of material, right? Where does it drive up the cost? The what? The detectors. Remember all these you need to plug into a detector, a photomultiplier tube, an avalanche photodiode, one of those things, right, to be able to convert the light into electricity. You need one readout per piece of scintillator, per segment of scintillator, right? So the more finely you segment, the more of those detectors you need. You may have noticed looking at your file that they're not that cheap. So there's it. And it's not just one per segment this way. Also, each layer needs its own readout, right? So you have 30 layers of this, then that's 30 detectors, right? Then you split it into 30 pieces in phi, then that's 900 detectors you need, right? Then you split it into 20 pieces in eta, and that's 18,000 detectors you need, right? So the number of detectors wraps up pretty fast. So you can't just make it arbitrarily small. But on the other hand, you want them small, right? Now, the good news is that you don't need to be as small, as like precise as you were with the tracker. Why not? Good, you're farther away from the center, so the particles are not more spread out. Plus, also, what are you not trying to do that you were trying to do with the tracker?
You're trying to measure energy and not position.
Right, you're not trying to measure momentum required with very careful curvature measurements, right? That a third of you had to suffer over. Here we just want to know energy, which is just hit the spot and move, right? So you don't need the kind of crazy fine granularity you did with a tracking chamber. But the smaller you can make the segmentation, then the more particles you have to detect. Especially if you have some kind of hadron collider, you're going to have a lot of particles coming out. So the segmentation is important. Okay, so when you segment it, we split it up in phi. So you imagine wedges that go around into the colorimeter. Each wedge is a phi section. And then you also split it up in eta. So you would typically split it up. So you take these things and you split it up like this, typically. Okay, it'll come out kind of in angles, and they won't be even. Now, the good news is you don't have to calculate that part. You just have to do the segmentation. Okay, the eta calculations are tricky, and it's probably better I take care of them. The same is true, by the way, in the end caps. Those also need to be split up in eta, right, as well as in phi. Yeah.
So we have to segment it in terms of eta, but then what is that?
Well, so let's talk about that. What are you actually doing? Let's talk about your spreadsheet. What are we actually doing? Okay. True words were never spoken. By the way, I made a mistake on your thing. I'm going to fix it shortly, but on your thing I put $6 billion. That's ridiculous. It should be $3 billion. Otherwise, you can just build yourself like a diamond palace, basically. It's too much money. So, yeah.
I disagree.
No.
I disagree.
Not yet. So, sorry, Maddie's question is an important one. If you have leftover money from the tracker, can you roll it over? No.
What?
I said no.
But you told us before.
But no,
You told us that it would
when
be...
when we hit the final detector, once you voted and made our chosen our final design, then I'll allow you to slosh money around between parts of the detector. But for right now, no, in the interest of, I don't know, fairness or something.
we can't wait for because we have like 50
now,
billion in our pocket.
So let's look at spreadsheet you'll need. This one is longer than the last one, and you'll want Excel, I think. I have it in Excel, so it'll work.
What?
And yeah, I did post the wrong one. Did I replace this? Post the wrong one by mistake, and I'm not sure if I replaced it.
I actually think he said
Yeah,
after fun time.
Oh yeah, we have that. I forgot we have that in the classroom.
Oh, it's not with it.
That might help.
Okay, here's,
You need
okay,
cataracts.
so here's a spreadsheet. Right, and it doesn't fit on the board for some reason.
Wonderful.
There's a weird thing that I have not figured out, and I just don't particularly want to. Is that better? Okay,
I can
so,
figure it out.
so it's the same basic setup as you've seen. Shape, can you guys read? Here, I can make it bigger. You have the shape, the XYZ coordinates at the center of the shape, which is often 0, 0, 0, but not always. These things I have to do double duty. Length, if it's something like a cylinder. If it's a disk, I realize there's an extra coordinate I needed for a disk that I didn't have implemented for the last round, so I have them now. Now the disks have to be hollow, they have to be like rings. If you're going to do a disk, it makes sense to do it as a ring. So this is the inner radius if it's a disk. Here it's the width if it's like a square or something, and it's the outer radius if it's a cylinder or a disk or something like that, and then the thickness of it. Okay? Phi and theta, as before, those are usually 0 because they're by default, everything by default is aligned along the axis, the beam axis. This is the material that the thing is made of, and so you have a drop down with all the basic ones, and you can add other things, like I said, by talking to me. And then here is the segmentation. So what you tell me is how many pieces do you want going around, right? So if you have a cylinder, this is the head-on view of a cylinder, right? The phi segmentation tells me to break it into 24 pieces going this way. The eta segmentation, this is the side view. The eta segmentation, so this is the phi segmentation. The eta segmentation tells me to break it into so many pieces this way. That's the eta segmentation. Okay? So in this case, this is from my old detector, so I put it in here. And there's phi going around, so that I want 24 phi segments and 10 eta segments. That's what that detector used. And then you have to tell it what kind of detector to use, what kind of photo detector. I did it all in acronyms because that was easier, right, than writing it all out. So photomultiplier tubes, multi-anode photomultiplier tubes, avalanche photodiodes, stacking photodiodes, right, I just abbreviated that. Okay, then the last column I said is just notes for yourself. The program doesn't read them, it's just for you to keep track of. So here's the thing, I deliberately made it so that you would have to put in all the layers individually. Okay, and then I give you this document so you can see some nice shortcuts to do it. Calculated columns in Excel are the key to do it, right? And so that you can very quickly run up a whole bunch of layers, basically that have the things calculated. But this allows you to change the shape of the layers with a lot of, like, if you want to make it, for example. Sometimes you might make just a whole bunch of cylinders like this, but some experiments have the cylinders get gradually wider as they go, gradually longer as they go down, right? So this would be a way you can control that. Each layer can be slightly longer, right? Yes?
Why is the disc hollow?
Why are the discs hollow? Because typically you need, typically you can't go, your discs can't go all the way to 0 because the beam height's there. And because what's the eta at 0? It's infinity there, so I can't segment it into, if it goes all the way, if it has a 0 radius there. So you need to make a hole in the middle so that it's possible to segment it in eta.
Okay, but as long as it's around the beam height, it's fine.
And it's not hitting your current tracking chamber, yeah. Yeah, we should have screwed these up so much, I hope. Yeah, it should be fine. So this document, as you can see, is long.
Good grief, Charlie Brown.
Yeah, I have 562 layers in there.
Oh.
Which is normal for a colorimeter. Yours will probably be more. But look, it's all filling with Excel, right? Or if you want to write a Python program to do it or whatever, that's fine too. So whatever. But use a computer to do it, right? I like, now you've all had CSI, so like the word computer should not scare you, right?
It scares me. It scares me.
I mean, it might like bring back like PTSD kind of things, but it should, like, you should know, like, be like, oh yes, I realize this is possible, right? In fact, I like Excel because I can work real fast in it, but if you're not comfortable with Excel, it might be easier to just write a simple for loop in Python or something and have it generate this. Yeah.
So, do you calculate the cost of all of these things?
I did, and I wrote up another program that will take this in. Now you have to copy it into a text file. One day I'll figure out how to fix that, but like it's not high on my list right now.
So that's how you got your radii, based on the cost.
What? No, the these? This actually, they do what I said. They get the radii just increased because there's a whole bunch of concentric cylinders, right? So the radii just increased by the thickness of the previous one.
Oh.
You see? Each one's just the previous one added to that thickness. So, yeah, there's a whole bunch of things like that. There's angle. If you want to do it, you want them to lie along a certain angle, you just do a little simple straight, and there's examples in here, so you can just copy if you want. Like I said, if it's and remember this, you have several people in your group. You don't all have to do this, right? So you can think about who is best suited to the task. You can draw straws or whatever. Okay, it's really not that hard to do. Once you figure it out, then you just drag it down. And you're like, okay, good, that looks right, and then you can drag it down and copy it into a text file.
Woohoo.
Okay. Now there's a caveat. There's a thing about the text file. It's not about text file. It's about the visualization program. The downside of doing this is that my visualizer now draws every single layer and every single segment of every layer, and it does it fairly inefficiently.
My computer was already breaking before this.
So I have a few ideas to maybe take this. So here's the basic thing. You can view it in, there's that opening screen
Low
that just calculates the cost?
That's the only
That's
way of
okay, so
viewing
that's
it.
helpful. Because then you can just get the cost and not worry about and if your cost is an issue, then you don't have to worry about the rest. If you want to actually view it, view a stripped down version right now. Because I've given it some thought. Of course, in real life, it is possible to simplify this a lot. But like with what I have right now and my current knowledge of 3D graphics, which is not very much, I can't come up with a simple way to speed this up. What you do is just take like the first and last layer of each part of your detector or something like that, so that you can just see where everything is, and then look around and be like, yeah, this is where everything is, and then just leave it at that. Okay? And then have a full version for the cost calculation. That's the best I can give you right now. I did all that last night, and it wasn't hard, because once you have the full version, it's very easy to delete rows from it. Just make sure to save the full version separately. Okay? And turn in the full version. Just use the stripped down one to make sure things are in the right place. That's the best I have right now. There is a way, of course, to accelerate these things. Computers are powerful, but I have to know how to program it right, and that part is not so good. Computers may be powerful, but Dr. Comics not. So that's the plan for that. Does that sound sensible? Yeah, does that make sense-ish?
Someone beat me over the head with a bat.
No.
Well,
Please.
what do you want to do?
3 years.
Why do I ask? That's kind of a dumb question. I don't mind. I mean, yeah, the extra I-Day is probably helpful, right?
Yes.
Okay, I can make it do Thursday. That's fine.
Okay.
But we will probably have. I can give you today and Monday, or we'll probably have to move on Tuesday. I'll check the schedule again, but it's tight, so I think we'll have to move on Tuesday. Okay, with like physics material. Like
You got it.
material. But I can give you till Thursday to finish the calculations and stuff. Speaking of calculations, another job is to actually calculate the energy, which is really, really important. How much of the energy do you actually pick up is a very big question. Or how much is actually absorbed. You'll never absorb 100% of the energy. That's not how it works, right? But you can absorb an awful lot of it. So in the document, I gave you a formula. It took me so long to find the stupid formula. I'm pretty sure it's the right one now. The formula is right here. Oops. And it's not the world's simplest formula. Okay? But it's this one right here. You don't need to see it from there. You have, you'll have a computer. You have this document. But X here is the number of radiation lengths, right? Which is to say, the length you're going divided by the radiation length of the material. Since most of you will have sampling calorimeter, I'm guessing, you'll have alternating ones, right? So again, Excel or something, right, or Python, however you want to do it, so you do a little to just figure out how much of radiation length has gone. Now, it's important. You cannot, X is the total number of radiation length that's gone through, okay? You don't start from scratch in each layer. It'll give you completely the wrong answer, okay? X has to be the total number of radiation lengths that has been through. And there's all this calculation you have to do. E sub C is the critical energy, which you just look up on the table that I gave you, that's down to the link at the bottom. Yes, okay.
Does the photo radiation length include in our tracker?
Including your tracker? It should, but let's not do that for now. Let's keep this independent of your tracker, except for the shape. Let's keep it independent of the tracker. That's a good question, but let's leave that out for now. Yes. Gamma? Oh, down here is a gamma. This is a gamma function. Excel can do it. Any math library can do it. Wolfram Alpha can do it. It's a standard. Who came up with gamma? Is that hang on? Whatever. Okay. Anyway, the gamma is sort of like an extension of a vectorial. It's a thing. You can plug it into anything, it'll do it, right? In Excel, it's called gamma, right? In Wolfram Alpha, you type gamma parentheses or whatever, right? And any math library will have it. Python's math, what's called ModPhys or other things called, we'll have it. Okay. So this tells you X is the total number of radiation lengths it's been through, but this tells you the amount of energy it's emitting at that instant. Okay, so it's the sort of thing you have to sum up over time, over distance rather, right? As you go through, you calculate it for each piece, and then you have to add them up. Yeah.
So when it says the fraction of the original energy, is it going to give us
It will give you a number between 0 and 1.
Oh.
Right, it'll give you a number between 0 and 1. So the energy spectrum looks like this. You start at 0. It looks like this. Okay? This is what that function looks like if you graph it. So the exponent A determines where this is, and A depends on the initial energy of the particle. You can use that same initial energy that you're using, that 1/3 of your center mass energy, right, as your target again. Right? It's a huge number, by the way, so you might not be able to hit it. But you want to use that to determine, you use that as your energy, right? E sub C, the critical energy you look up for the material. And then everything else, you just have to, so basically you're calculating this at different points. You're basically doing a Riemann sum. You guys know Riemann sums? Some of you, probably some of you do. All you're doing is favorite thing in the world, right? What you're basically doing is you take this equation. I should name the equation. So that equation is, let's call it F of X, right? You calculate this equation, and so the energy loss is that, or the energy fraction loss is that equation times, so the energy loss, yes, the energy loss is this equation times the thickness of whatever you just went through, okay? Times the original energy, or times the previous energy, right? So you have a certain amount of energy, so it's an iterative process. You calculate this for one layer, right? This function times the thickness times the energy you had before. Then that goes into the next layer. This gives you lose some energy. Then you go to the next layer and you figure out how much energy you lost from there. Then the next layer you figure out how much energy you lost from there, and so forth. Hang on, is that true? No. Sorry, that is the original energy. Makes it easier, actually. Yeah.
The f of x, which one?
F of x is that thing up there.
The a equals
No, the x to the a equals to negative x over 2 over 2 to the a plus 1 gamma a plus 1. Where a equals all that. Yeah.
Is there like a number that we should be getting?
Is there a number you should get? Yes. Okay, that's a good thing. Typically, you aim for 20 to 30 radiation lengths or interaction lengths. You have higher energy particles, some of you in particular, depends on the varies with the group, right? So some of you in particular are going to need to build cheaper, bigger detectors or with thicker absorber plates to absorb more of the energy, right? Because some of you are going to, but basically, you want to, the more radiation lengths or interaction lengths you can get, the better. Now remember, you have two pieces, your EM count and your hadronic count, right? You should call them E count, H count. You do this with the radiation length calculation only in the E count. You want it to be finished by the end of the E count. And then you do it again with the interaction length calculations, but with well, I guess you can put the E count, will add a little bit. And then with the H count mainly, right? So you do it once with radiation lengths, you do it again with interaction lengths, but that gets much longer because interaction lengths are much longer than radiation lengths. That's the one, that's for the hadronic color. Okay, once you've done it once, the second time should be easy. Okay, you're all giving me this look. Let's just, I think it's probably best to just work on it. Oh, but there's one more thing to add. Little side thing you can decide if you want, okay? There's a special kind of calorimeter. Remember I told you hadronic calorimeters are really hard because when they have those nuclear collisions, you lose energy, you just can't measure it, some of it, right? And that makes it hard because the amount that gets lost is not consistent, and so your energy measurement like loses quality, you lose resolution. And so there is a kind of calorimeter called a compensating calorimeter. And while there's different ways to do it, the most standard one for high energy physics is to use uranium as your absorber. Why uranium? Well, what do you know about uranium?
It's radioactive.
It is very dense, but what else? It's radioactive. Good. That's because its nuclei are unstable. So when you hit a uranium nucleus, it can make it fission, it can make it break apart, and when it does that, it releases more energy. So basically, if you build it carefully out of uranium, you can release energy from there that compensates from the nuclear energy that's lost in there. Remember I told you lose some energy? A compensating calorimeter releases other energy to compensate for the energy you lost. It improves your energy measurement. What's the downside? Uranium is, no, it's not. Who cares if it's radioactive? But uranium is expensive. We use depleted uranium, which means energy after you extract all the uranium-235 that they use for nuclear reactors and bombs, and then everything else is depleted uranium, low radioactivity, and not useful for any nuclear applications, but useful because it still has its unstable nuclei that you can use for compensation. Okay, depleted uranium is expensive, but you can do it because it gives you this extra energy measurement. Yeah.
So why do the hadrons lose energy?
When they hit the nucleus, there are a whole bunch of very complicated nuclear interactions. Sometimes what happens is they call nuclear recoil. So it hits the nucleus and kind of bounces off, and the nucleus goes a little
What's our budget?
and kind of stabilizes. And there's no real energy. The energy is lost as heat, which you can't measure, right? And sometimes when it interacts with the nucleus, neutrinos, those are lost too. Those are the main ones. And sometimes the neutral prions you can still catch. So there's a few of these decays that just get dispersed as heat, and then you can't catch those. And so a compensating calorimeter replaces some of that lost energy and allows for a better, because it replaces it in a way that's proportional to how many interactions there were, and therefore it replaces it the right way, so you can get a much better energy measurement with those guys. But they're very expensive, so you'll have to make that trade-off yourself. Okay, better to start working on it. Asking questions, I think, will be more helpful at this stage. The visualization with the calorimeter is up online as well as is the Excel document, as is this document. You have jobs, you can split them up. Remember, you should be in rotation, right? So you're not only doing the same thing last time. Let's talk about it. Ask me questions.
Do you want to do the energy analysis or do you want to do the description?
Right, but it's you don't have to lie for the stuff that comes out of all sorts of stuff.
guys.
David, do you want to do the description?
Okay.
Okay, so what's the description
The
to
photon are reduced to anything else. There will be some nuance, don't worry about those.
So we're gonna make this.
This stuff.
I believe our magnet itself is actually a cylinder,
That's
so
the
we're just gonna make
the
this
final part is the
cylinder.
neon detector.
So we have a circle surrounded by a cylinder, surrounded by a cylinder.
Yeah, the particles are
detector
colliding.
design is gonna
Don't
be
affect
formed.
the
Yeah, multiple circles.
What?
Don't we have multiple circles? Oh wait, no.
A circle. It's just a pure circle. No, a sphere. I mean.
So confused about where our detector needs to be. Like, it needs to be in our, our tracker needs to be in our, what is this called? Calorimeter. Why can I not remember this? Calorimeter needs to be in our computer, right?
The detector.
Okay.
Someone send me the full thing.
So,
I sent you
we
the
want to
full
have it
text
be a
file.
cylinder, or a disc, or a sphere. All those
that you're putting into the program at the end.
Oh.
Someone send it to me.
Okay. You can get that straight off of the Excel file I sent you, but
And by the way, there is one more detector on the outside. The neon detectors go on the outside, so
dagnabbit.
so you can't make it arbitrarily big, right? The bigger you make it, the harder it is to build a neon detector.
So, I'm thinking if
You
we
have something
put
from
this
there, that'd be really
into
good.
the tracker and magnet, that would be good. So we'll probably have to use graphite.
Wait, shoot, does that mean that we need to
or depleted uranium.
You can build up with it. Buildings up, hammer is not
Yeah, it's pretty small. We have
Yeah, the main ones are fairly small. And our detector is like 5.
Matt,
It's not even like meter, it's like
It was like
0.25.
You're M cups.
yeah.
That's like
Coats? Okay.
that big?
Yeah,
That's
probably.
just about, maybe a bit bigger. Our tracker needs that to contain that.
That's crazy.
I think that we can do it.
And our magnet is like 47.
Just gonna stand and watch
Oh yeah,
you.
it's 600 Tesla.
And that's alright.
That's
I love the
600
way it feels. Just gonna stand and hear you.
I haven't done the description yet.
We just have to know that we have to add 6 meters at the end of that the entire night. So calorimeter, okay. First of all,
Alright, it's sent to you.
we have 3 sequence cases: argon, lead tungstate, and plastic.
Right, so it doesn't have to be, it doesn't have a radius, right? It really just does an angle. Right, so when it's changing, but you get an angle.
So plastic, argon, or what?
Eden, stop being so loud.
So the angle is one way.
Let me pull the mic out.
What?
So you have 2 angles. So one angle is
I think go ahead.
Jesse,
What's
you
the
say
best,
all of
most,
those.
let's choose the best, most expensive option. That's got like
Tungstate and
pretty far.
depleted uranium.
Yeah, that's true. Our stuff is like really small. It's like the density of
Good. Can you go ask Peter? If we can please use the 22 billion left over from our calorimeter.
Why do you have $1 billion? Because we thought we'd be able to use it for other stuff, but we were wrong.
And the fact that we had so many issues with getting a particle accelerator built that
Why did
at
you
the
need
end of
to-
that we just
What the issues with getting it built?
That was a funny day.
one of our members was sick and one of our members left in the middle of a project.
Yeah.
But still, like, who was covering the calculations? Yeah, you should have been able to calculate.
I did, but I didn't have any comparison because comparison was in charge of doing the calculations for the energy maps,
Yeah.
the resolution maps.
When it sucks to be.
Sucks to be
It always sucks to be
You
me.
guys get in trouble visualizing calorimeter, look up some pictures of
Ask him.
Look up, CMS calorimeter or Atlas calorimeter, CDF calorimeter. Those are some of the
Personally, no,
big
these.
things. You can get some pictures of it. Don't just write calorimeter, we'll give you like chemistry stuff, right? But if you write in the name of the experimental calorimeter, you'll get a bunch of pictures. Give you an idea.
So my job's like.
Yes.
Oh, shit.
Expensive as
It is. Let's do a large colloidal apparatus. Let's
So we're
do
doing
that.
depleted uranium and lead tungstate.
Make sure your photodetectors can handle the environment.
Which one is better?
You need both electromagnetic and electronic detection.
Better, but the electric.
You need to stay under budget.
This is a scintillator. This is
And as always, creativity counts.
Oh, yeah. We're gonna-
Screw you.
We have to vote.
How am I supposed to be creative during this? I refuse to make a spherical
Draw a smiley
calorimeter.
face. Draw a smiley face on it.
Actually, would that make my life easier?
The spherical calorimeter wouldn't be the most painful thing in the world because you would have to do it in decreasing amounts of scintillator.
Make your thoughts
So you can,
like 3D scan everything.
that's both a horrifying idea because it would be such a incredible calorimeter design.
Yes.
But it is Dr. Doll. So
It improves the quality by 100%.
If it's big enough, then it'll all be fine. It's gotta be like really big.
Or we could just move up one.
Like it's not a statue of Dr. Doll.
What if we made a calorimeter that was one atom big?
I want a flipping budget of
That
6
wouldn't really help
million.
anything because it would be like an atom. That's not a thing. That's not how. That's not.
Okay, I didn't know how to
So
stretch
place
the cover.
plastic scintillator.
You gotta imagine after 20 years.
Who's doing what job? We should probably
Yeah, okay.
determine that.
There's 3 jobs.
Well, no, because even if
I
you're
think I know what job
a
no
million
one's
calorimeter, or a million calorimeter, even if
16.
a million interactions, let's say you have a writing constant, you do a million interactions per year.
Nolan, we got to determine.
But it's a lot more. It's a lot more than that.
Nolan, let me guess your job, energy analysis.
What job do
What
you
job
want?
do you want? Either Excel/text file about where everything is, the standard paragraph of what it is, or the map.
So wait.
I don't know. You pick.
I'll do energy analysis. So you get to build work.
Got wrecked. Hey, but that means you get to work with me with rather stuff.
So the thing is though, I'm the one who has to actually comprehend it.
That's true.
I'm the person that gets to sit on the edge,
But Nolan,
wait until everyone's done their work.
Nolan, me and Eden also have to comprehend the stuff because we have to actually make the calculations sort of thing.
I have to comprehend this stuff so that because I don't trust any of you 3, and I have to make sure that you're working like that.
Wow.
I'm now a part of your group
That's
again.
fair. So I'm doing the text files?
Yes.
Wait, I need to look at all the stuff I have to do. I should make up the test on Monday.
Okay, fine, Benji. Which one is this for? Because what we're supposed to do is we're supposed to do it intermediate between scintillator,
Not scintillator, scintillator.
You notice how in the middle there is the tracker? You have to have a tracker at the very, very center. With wires of scintillator and absorber around. So you have a tracker at the very middle. That's where that thing's actually getting numbers.
Wait, don't you already have the tracker? That was the thing we built earlier that measured the momentum.
Why the hell?
That's why I got irritated. That was a detector, not a tracker.
What the crap? What's the difference?
If I could answer that question.
It's tracking the text. There's some kinds of detector.
And why that says detector?
So wait, where do you stick this on the actual thing?
In your
In the middle.
Just straight in the middle?
Yes.
What?
Ask Dr. Dong. I'm confused about why this is detector. I'm confused. It keeps being a detector.
Okay, I will.
I'm still confused about what the purpose of this is for. This is to calculate energy. What's the last thing to calculate energy? Momentum.
Decide what weekend this would be like. This weekend, like the next weekend. So,
He can see.
and waste most of his day yesterday.
Benji, you're wrong.
Or go to Woodman's.
What?
They're not in the middle, you
We need
idiot.
to have energy drinks to stay up all night.
It's like,
Well, what are they used for?
So what they're used for is you have your scintillator thingy
All about the comfort.
Scintillator! It's scintillator!
He's gonna open our quad door.
So you have your scintillator.
He just did it to trigger.
Well, yeah, I know.
Yeah.
It worked well. Anyway. So what is the purpose of the actual scintillator?
So the scintillators are connected to the optical fibers.
Okay.
And those are connected to these, which is off to the side, and it measures the intensity of the light. No, you can't have it in the particles aren't going to collide with anything but the
How
thingy.
we're supposed to be.
That's what I have a problem with.
It's vaporized. It's vaporized.
No.
Okay. It doesn't. I'm guessing you want the most expensive one.
Yes! All of the expenses!
Quiet. Lower your volume by 80%. Too late. I already did.
I refuse to write out each layer individually.
Show me the money!
I already have.
That's another good
Benji, you tap the one hand, I'll tap the other. Benji, come on. You know you want to tap the one hand, I'll.
Why? What cult is this?
Don't worry about it.
This is the tap.
Don't worry.
This is the tapping tag cult.
Oh my god. Tag, you're in.
Tag, you're in.
Did you just assume my pronoun?
Yes.
Tag, you're in. What are you doing?
Nothing at all. Don't worry about it.
What is that?
Are you caressing your leg? No.
Do you know how to do Python?
Yes. You do all the work.
I know how to do Python as well.
Yes.
Screw it. Hey, let's bring it to Conquer and have him write it for us.
Oh my god.
Screw it. Let's write this in C++.
Don't do this to me.
If I knew C++, I'd be working on the console here on SolidWorks SIR right now. But I don't know C++.
I did C++.
You were accepted for that SIR, right?
No, I got rejected.
That literally came to instance.
By the way,
For that specific experiment.
we don't have to worry about playing.
It's still possible to do it.
Take a sphere. We don't have to worry about playing.
It's still possible to do it.
To what, work on CMS? What do you mean? You mean by breaking in and stealing all the data?
Why you do it as a senior and then like take a year off or something like that?
You can still do it as a student.
Yes.
Uranium is not possible.
Chill, Ethan. Chill.
Don't tell me what
Lead
to
is the
do.
most.
No.
Take a chill pill.
Shut up.
Take the blue pill.
I am going to take as
Don't
many
take the red pill.
as caffeine pills as I want.
Yeah,
No,
lead is the most
don't do that.
What was the difference between blue pill and
Really?
red pill?
Why?
If you compare radiation length,
I'm glad you got the
for
reference.
all of them, the interaction length is 80%, or radiation length, it has the lowest.
Shut up, Eden.
It's not a clever reference.
Basically, it's more than 3 times.
Yeah, but the uranium is a secondary component.
Would you be mad if I stabbed you in the arm with pencil?
I'd be upset and
Oh, it is
disappointed
also
with you.
compensated.
Guess I thought you were better than that.
What's the whole point of using
Yes.
with uranium?
Yeah, I'm scared.
I don't know. Yeah, okay. I'm glad that if we use liquid argon, we have to have an extra.
Why would
10
you
centimeters.
use? Stop using liquid argon.
So we can't use photomultiply tubes, obviously,
Why not?
Yeah, we can.
because magnetic.
Oh yes, don't do that.
Which one's not susceptible to radiation?
Avalanche photodiodes and vacuum photodiodes.
So these two. The not as expensive ones.
Oh, atomic properties of more than 300 materials.
And we could always go with multiple multi-anode multiple.
Cannot put it back there.
You can just have it off to the side outside the magnetic field.
What are you gonna? What are we supposed to use?
It's anyway.
Oh,
I was trying to draw a flower.
Why are you?
It worked on that. That's just a B now.
flipping.
Why are you drawing on people's computers? Okay.
So we've decided that
This isn't even my computer.
We're gonna be using
Yo.
I said scintillator. You back to
Scintillator.
I know!
back to
That's why I keep...
It makes her lose her mind instead whenever we say scintillator as it's properly pronounced.
But then you started doing it on accident, and that's where I get worried.
Not good. Back to
Scintillator.
Anyway, we're using light comes to the scintillator. Let's do it right now.
I gotta get my skin on this later.
The proper name is Wolferennial. Yeah, it's on the
Okay. Now here's my question for you. What is the stopping energy of this? Of argon gas? Are you sure?
What is the power of argon?
Plasma energy is this. Did you just say the power of argon?
The power of
Wait, do you think we're using argon liquid, right? Or you guys are using it?
We're using lead tungstate because we have a lot of gas.
all of the money.
Wait, how do you have all of the money?
We have, let's see, how much? We have $20 billion left from our previous
We can use the extra stuff?
No.
Screw you.
I wish. Otherwise, we would just have, like, the most. We would split the $20 billion left between the three of us. Screw this part of the sector.
We could have done 22 more but no.
No, we couldn't have. We could have done one more.
Wait, we're going to
We have done one more thing.
We had like
Well, crap.
Two more, because two of them, actually, yeah, two more, because two of them cost half the budget. Because if half the budget is left, it would save us with that amount would be equal to two.
What if you had
Total multiplier 2.
I thought the entire thing was a synchrotron, not each individual one.
So, let's focus on the first step. What's the first step?
Figure out how big you want it.
Okay, well, how big
I would
you
do that.
Figure out how big you need it first.
$5 per hour.
No. Figure out how big you need it first.
first we need to find out the energy?
Yeah. So, wait. The energy, you're supposed to do it at 2/3 of what your actual thing is.
1/3.
I heard 2/3. See, I did 2/3 for my 22 T.
what?
20 TeV. And that was 1/3. So we have about,
Yes, but think about mine is 4 times bigger.
I live and I
used to go and work.
we use half our money. So ours is just more cost effective, it's better though.
That's not how it works.
I don't know how big
Mine resolves several issues within the physics department. Can you say yours does that?
I don't know. That wasn't my job to figure out. That wasn't my.
Can you do photon, anti-photon?
Yes.
Can you do photon, anti-muon?
No, we cannot.
With you. How about photon, muon?
No.
Well,
We don't have the setup to interact between photons and muons and photons.
I do.